In this video, I'm going to be teaching you guys how to use a proof by contradiction to solve these two statements, to prove these two statements on screen right now. So let's go ahead and cover the first one. So the first thing that you want to do when you're doing a proof by contradiction is write this down in conditional form. And the reason why you want to write this down in conditional form, your proof in conditional form, is because you're going to be negating this statement. And if you write this down in conditional form, you can use the laws of propositional logic. So we have if x is irrational, then the square root of x is also rational. This is exactly what we're proving. But here's the thing about the proof of contradiction. You have to negate this. So this stands for the negation symbol right here. Right? And here's the thing. We can't negate a conditional, but what we can negate is an and or statement. So here's the thing about x, square root of x is rational, or square root of x is irrational. So this right here is the conditional identity, correct? If we have a statement and then a conclusion, P dash Q, the conditional identity turns P to not or Q. And that's exactly what I did here. I negated P, right, to get x is rational from x is irrational, and I just left Q the same. So the square root of x is irrational, correct? All right, once this is done, what do we do? Well, here's the thing. We can use De Morgan's theorem. So we can distribute this negation throughout here. If we distribute this, we need to flip the operator as well. So we have x is irrational again, right? We're negating this statement via De Morgan's theorem. We're flipping it with the and operator to get the square root of x is rational. So this is what our new statement is. X is irrational and the square root of x is rational. So this is what we have to assume. This is our assumption. Remember, our assumption just came from negating the original statement. So let's write this down. Assume for the sake of contradiction, that, and I should write this smaller because I might run out of space, as that x is irrational, right? And this is our assumption down here. So this is what we're assuming. X is irrational. And this is the and operator. And the square root of x is rational. So what does a proof by contradiction do? Well, what it does is we assume the negation. Okay, we assume the negation of the original statement. And if something impossible happens in the negation, then that means the original statement must be true, right? If the negation is false, in a mathematical sense, this is not for everyday logic, but in a sense, in the context of proofs by contradiction, if the negation is false, right, something impossible happens in the negation, which I'll show you, then that means the original statement must be true. Okay? So first things first, we have x is irrational, and we have the square root of x is rational. Well, we can't really define irrational, but what we can do is define that the square root of x is rational, right? And we can do that by the definition of rational. The square root of x is equal to a over b, where a, b are integers, ints, and b is not equal to 0, right? It wouldn't make sense if the denominator was equal to 0 inside of a fraction. All right, once we have this, what do we do? Well, remember, x is irrational. So how do we turn the square root of x into x? So we can do something, so we can compare these two. Well, we can square this, right? So let's do this. Let's just write down with some algebra. With some algebra. Okay, we can write down the square root of x is equal to a over b. And we could turn this into the square root of x squared is equal to a squared over b squared, where b squared is not equal to 0, right? And here's the thing. If you square a square root, you simply get the original answer. Or what's inside the square root, sorry. You simply get what's inside the square roots, right? So we have x is equal to a squared over b squared. Here's the thing. Multiplying ints gives ints. So a squared and b squared are also ints. Here's the thing, though. If x, right, can be defined by an integer over an integer, doesn't that mean it's rational? Right? By the definition of rational, x is also rational because we can express it as an integer over an integer. Here's the thing. X is irrational. That is one of the assumptions we had at the beginning. Therefore, this is a contradiction. So we can write down by the definition of rational, x must be rational. Here's the thing. This is a contradiction. Contradiction. Because x is irrational. That's what the assumptions we had at the beginning. So this is a contradiction. Therefore, and we can write down the original statement now. If x is irrational, I think, you know what? I'll write this on the next line. If x is irrational, then the square root of x must be irrational as well. Okay, let's go over this. All right. So we assumed the negation of the original statement, right? And we had to use the conditional identity and the De Morgan's theorem to get the assumption. And our assumption stated that the square root of x is rational and x is irrational. So what do? Well, we define the square root of x as a rational number, which is an integer over an integer, right? An arbitrary integer over an integer, a b, where b is not equal to 0. And we squared this, right? We squared this right over here to get x is equal to the square root of a over the square root of b. Here's the thing about that. X, after squaring, right, the square root of x, is rational. A squared over b squared is the definition, right? These two are integers, is the definition of a rational number. Correct? So we wrote down multiplying ints gives ints, therefore a squared and b squared are also integers. By the definition of rational, x must be rational. Okay? But here's the thing. This is a contradiction because we assume that x is irrational. So the whole point of a proof by contradiction is showing that something mathematically or logically impossible happens in the negation. And if that is the case, then that means the original statement is true. Okay? And that's what we conclude at the end. This is a contradiction. Therefore, if x is irrational, then the square root of x must be irrational. So remember, the first thing you do with the proof by contradiction is write down your assumption. So let's go ahead and write down this assumption. Right? xy is even. This is the original statement, not the assumption yet. Dash, that means x is also even, or, so this is the or operator, y is also even. Okay? And remember, the assumption for a proof by contradiction is the negation of the entire statement. So what do? Well, we can use the conditional identity to get not xy is even. Therefore, that means xy is odd. Correct? Dash, sorry, not dash, or x is even, or y is even. Remember, this is the conditional identity, right? We negate the hypothesis, put an or operator in between, and leave the conclusion the same. All right, this conclusion is the exact same. And we just turned the conditional, the little dash, into the or operator, and we negated the hypothesis. Hypothesis? No, condition. Wait, I think you can call it both hypothesis and condition. But xy is odd, right? This is the negation of the original xy is even, correct? And now, here's the thing. We can remove these parentheses because everything is with an or operator, correct? So every statement is separated with the or operator. But here's the thing. We can use the De Morgan's theorem to distribute this negation into the statement. De Morgan's, right? So we negate this statement, x is even. And remember, when you use excuse me. Oh, I just burped. When you use De Morgan's theorem, you need to flip the OR operators into AND operators. So X is odd here, and X is odd, and Y is odd. Okay? So this right here means X is even, and X is odd, and Y is odd. This is our assumption for the proof of contradiction. So let's write down the assumption at the beginning of our proof. Assume, let's write this down smaller. Assume, for the sake of contradiction, that's how you spell it. Contradiction. Let's actually move this down because I need to write something above this. Assume for the sake of contradiction. Hold on, let me remove this. OCD, my OCD is kicking in. Assume for the sake of contradiction, XY is even, and X is odd, and Y is odd. All right. And let's write down, let's introduce the variables. Let X, Y be integers. All right. So I need to introduce the variables we're using. I forgot that in my proof of contrapositive video for like 2 out of 3 of my proofs. So I'm not going to do it again. But assume for the sake of contradiction, X, Y is even, and X is odd, and Y is odd. Okay, so here's the thing. X, Y is even, right? But X is odd and Y is odd. What do we do? Well, there's a couple paths that we can take, right? We can define X is odd and Y is odd, right? So actually, I don't think there's a couple paths. Never mind, throw that aside. But let's write down by the definition of odd, X is equal to 2k plus 1. Let's write that a little better. And Y is equal to 2j plus 1, where kj are integers. And you might see kj with this symbol, right? With the weird z. This also just means the same thing. This just means kj are integers. Now, if you haven't learned that notation yet, I'm going to make videos on that. Do not worry. All right. But let's continue on with this proof by the definition of odd. Actually, I think they do cover. They covered this symbol and this symbol. This stands for integer, by the way, in a discrete math course, right? I think they covered the subsets portion or the sets portion. That's besides the point. I'm literally losing track. Okay, by the definition of odd, X is equal to 2k plus 1 and Y is equal to 2j plus 1, where kj are integers, right? These are the definition of odd numbers, so we can define as such. All right, and we can multiply them together now. So let's say by algebra, and this is probably not proper grammar, but by algebra, xy is equal to 2k plus 1 times 2j plus 1. And we can also distribute this. We get 4kj plus 2k plus 2j plus 1. Okay? All right. Here's the thing, though. We can factor out a 2 here. So let's write down the next line. 2kj plus k plus j plus 1. So we factored out a 2 out of these 3 front terms here. Here's the thing. Multiplying, I keep spelling wrong. Multiplying and adding ints gives ints. So 2k plus 2kj plus k plus j is an integer. Ugh, writing down. Bad line, bad spacing. All right. Well, by the definition of odd, xy is also odd. All right, how did I come to that conclusion? Well, I determined that 2 times k times j plus k plus j is an integer. Well, what's the definition of an odd number? What was that? What's the definition of an odd number? Well, the definition of an odd number is 2 times some integer plus 1. Here's the thing. We assumed that x, let's use a different color, x and y are odd numbers. We multiply them together to get this monstrosity, And we factored out the 2 to get this guy right here. Well, here's the thing. This right here represents x times y. That is assuming individually x and y are odd. But if we multiply them together, what do we end up getting? We ended up getting another odd number, right? If you multiply 2 odd numbers together, then you get an odd number. But our assumption assumed that xy is even. And by the definition of odd numbers, xy must be odd, right? Because it's 2 times integer plus 1. Therefore, this is a contradiction. Contradiction. Right? This is a contradiction. Right? xy is also odd. That's not what we assumed at the beginning. Therefore, this is a contradiction. Therefore, if xy is even, then x is even or y is even. All right. So remember, proof by contradiction. You need to start off with an assumption, and the assumption is just the negation of the original statement. In order to find the negation of the original statement, you need to use some laws of propositional logic, like the conditional identity and De Morgan's theorem. But besides that, you just need to show that there's some logical contradiction with assumption. Like, for example, in this proof, we assume that x is odd and y is odd. We multiplied them together to get xy, right? And we showed that xy is an odd number. Here's the thing. Our assumption stated that xy is even, and this is a contradiction. Therefore, the original statement must be true, right? If the negation of this statement is false, then this statement is true. Okay? So that's really it for the video. If you have any questions, put it in the comment section. And if you found this video helpful, consider subscribing and liking the video. Thanks for watching.